Okay, last time we discussed dimensional analysis. So suppose there are a number of physical variables involved that are involved in the problem that you are interested in. So let's say A, B, C, D, E, and so on. So in that case, you can represent, the relationship between these physical variables. For example, A could be, the drag, and then we can write this as a function of the rest variables like this. But since there are so many physical parameters involved in the problem that you are interested in, so in the example that we took is drag on a sphere in a uniform stream. In that case, drag is a function of the radius of sphere, fluid property like density, viscosity, speed, and so on, right? There are too many physical variables involved. So instead of using original physical variables, what we tried to do was to combine these physical variables to form dimensionless pi terms. Okay, so in that case, you can write the relationship between physical variable in terms of dimensionless pi terms, like something like this. Okay. And depending on the problem, there you could have many dimensionless parameters, and sometimes you have only two dimensionless parameters. Then the problem is easier. Otherwise, you can write the relationship between pi terms in this way. As you saw, in the last lecture, for the sphere in a uniform stream problem, you have only two, dimensionless parameters. What was, the drag divided by rho u square r square type, pi term, which we call pi 1, or we can call, drag coefficient. And in that case, this drag coefficient depends on only one, pi term, which is a Reynolds number, basically. So in that case, the Reynolds number can be written in this way. Okay, so this was Reynolds number. And if you have more, physical variables involved, then you could have, more, dimensionless terms. But this is a much simpler relationship, although we don't know what f is. Okay, whether this is linear, nonlinear, we don't know. Okay, so the only way that you can find what f is to solve the problem analytically or numerically, or you can do the experiment and to find the functional relationship between CD and drag. As I plotted last time, you could have something like this between drag and Reynolds number. Okay. So far so good. So last time, I at the end of my lecture, I talked about similarity. So to get the drag, so suppose you are interested in drag on a surface ship, then you cannot do the real experiments with a real ship because it's too big, and also you typically do the experiments before you really build the ship, and therefore you need to do some experiments. And so what you're really interested in is drag applied on a ship. And then what we know is drag coefficients of ship will be the same as, drag coefficients of model if Reynolds number that the ship is operating is equal to Reynolds number of model. That's the the consequence of this. Because the drag coefficients only depends on Reynolds number. So, it doesn't matter, whether you are looking at a real ship or a real model. As long as you match, the Reynolds number, drag coefficients is the same. I'm not saying drag is the same because, the real ship has a larger drag, but drag coefficient, which is dimensionalized with respect to this. Okay. So the real ship is has a larger dimension, and so its drag is bigger. But when you non-dimensionalize, drag coefficients are the same as long as you match, Reynolds number. Okay. But quite often, the drag, or in fact, the drag doesn't depend on one parameter, for example, Reynolds number. But also, it depends on, other physical, parameters. Typically for surface ships, drag coefficients would be a function of Reynolds number and typically fluid number. Okay. Fluid number is another, pi term that you can get if you include, gravity in the problem. Okay. So whenever you have waves, the gravitational acceleration, gravity plays a role to generate the waves. If you don't have, gravity, you don't have the waves. Okay. So there are another, physical parameter which is g. So another pi term would be, like a g divided by some combination of repeating variables. I don't know if you still remember that. This is how we construct, pi terms. To construct pi terms, we choose 3 repeating variables out of variables that are involved in the problem. When we choose, 3 repeating variables, we choose them so that they have, the fundamental dimensions m, l, t, which are the mass, length, and time. Okay, so you find a combination. So last time, we chose, density and velocity, and for example, radius or this time, length of a ship as a repeating variables. Then we chose, alpha, beta, gamma, such that this guy is a dimensionless, meaning that the dimension of this pi term would be this, right? That's how we chose, alpha, beta, gamma, because we have 3 unknowns for 3. We have 3 equations for 3 unknowns, and you can determine alpha, beta, and gamma uniquely. And when you go through this, then you realize the pi term that you are looking for is okay. And the reason is G has a dimension of L over T squared, then multiplied by L. So dimension of numerator is L squared divided by T squared. And U has a dimension of L over T, and you square that, and then you get the L squared over T squared. So this is dimensionless, parameter. So you don't have to really go through, this by just, doing inspection. That you sometimes, you can get the pi terms. Okay. But if it's not clear, then you go through, formal procedure. But sometimes you can easily guess what the pi term you will get. And this is basically, one of our Froude number squared. So here, Froude number is defined typically U divided by. Yeah. So as I said, drag coefficients not only depends on Reynolds number, but also depends on 1 over Froude number squared or Froude number. Okay. So that's what I wrote here. So whenever the waves appear in the problem, then you have to include gravity as your physical variable. You include gravity in your dimensional analysis. One of the problems here is when we match Reynolds number. So we match the Reynolds number in this way. Then as we discussed last time, so we have a ship here and model here. And if you use the same fluid, this and this are the same as this and this, right? And then typically the length of ship is much bigger than length of model. The speed of model has to be much faster, okay, to match Reynolds number. But on the other hand, if you match Froude number, then what happens is once again, the reasons why we are matching, these two Reynolds number and Froude numbers is when you have this, then you have drag coefficients for ship is the same as drag coefficient for model. Okay, since we know this, we are trying to match these two. So based on Reynolds number scaling, we know UM has to be much faster than UL. US, U ship, right? But on the other hand, if I look at this guy, if I want to match, the Froude number, then what happens? Gravity doesn't change. You're not going to do experiments somewhere else. You're going to do experiments on the Earth. So G, gravitational accelerations are the same. And then this guy is bigger than this guy. So US has to be bigger than this. Okay? So meaning that you model. Okay. So we have a contradicting information here, and so that's one of the difficulties that you could encounter when you look at the problem that gives you something like this. Okay. So when drag coefficients depends on Reynolds and Froude number, and what you typically do is you neglect one and then you match the Froude number to the experiments, and then after that so that is not really correct, but in practice this is quite often what you do. But there is a big question mark there whether you can split in this way. Maybe not. But for practical applications, that's what we do. So it's still open problem, how we solve this problem, because it's too complicated. Even without dependence of Froude number, solving finding this relationship, numerically is really, really, difficult. In particular, when Reynolds number is large. Typically, Reynolds number is large when viscosity is small, which is true for water, and when length of object is large. Okay, so typical Reynolds number could be 10 to the minus 7th, 8th, 9th, and which is a really big number, and then the problem becomes very difficult. And so it's not easy to include both Reynolds number and Froude number to find a single functional relationship like this. That's why we split that way. Okay. So any question? Okay. The other way to do the dimensional analysis, when you solve Navier-Stokes equations numerically, is through non-dimensionalization. Okay, so that's what I'm going to talk about today. So it's a non-dimensionalization. It's a simple, the concept. Just like, finding pi terms, you want to use, dimensionless variables, to solve, when you solve, the Navier-Stokes equations. So let me write down Navier-Stokes equation first. Okay, so this is a Navier-Stokes equation. Of course, we have to solve. In addition to that, we have to solve, the continuity equation, which is this. Okay. So then we have a complete, set of equations for velocity u and pressure p. Also, I divide by rho, dividing the left and right hand sides by rho. So I have 1 over rho here, and instead of mu divided by rho, I use kinematic viscosity nu. Okay. And also you might have a gravitational acceleration g here, which is body force. So here, each term has a dimension. Okay. And so to non-dimensionalize this problem, what you need to do is the following. So first of all, you have to choose characteristic, once again, length scale and time scale. Okay. So first one is choose, characteristic length and time scales. So, for example, if you solve a problem of a sphere in uniform stream, then it's obvious. Characteristic length is the radius. Okay. And so I use L. And the characteristic time scale is something that has a dimension of time. And since for the same problem, the dimension of time can be obtained when we divide L by U. Okay, because this has a dimension of length, and this is dimension of length divided by time. So I have a time in the denominator. So at the end, this guy has a dimension of time. Okay. So this is my characteristic length, and this is my characteristic time for the problem. Once again, this choice these choices are not unique. You can choose different variables to make k-trace length and k-trace time. But the problem that we discussed last time is almost obvious. With what you have to choose for k-trace length and k-trace time scales. Or you think this k-trace time, this is L, right? And speed here, U. So this is typically the time to take when a fluid particle goes from here to here, basically. Okay? Because if you multiply by that time by U, then that has to be actually 2L, right? The diameter. And so this is actually half time, but that measures the time scale of the problem. Okay. So after that, then you just non-dimensionalize all the variables. Okay. Non-dimensionalize all the variables involved. So instead of U, I use U star, which is it should be dimensionless. So to do that, what I do is U is a vector divided by characteristic, the speed, or you can think this is a characteristic length divided by characteristic time. So then this is characteristic speed, which is nothing but U. Okay. And then X has to be non-dimensionalized with respect to what? Characteristic length, which is L. Time can be non-dimensionalized. So in other words, we divide by something, this guy will be dimensionless. So to do that, I have to divide by characteristic time, which is L divided by U, which is here. Okay? And then P, that's another physical variables or dependent variables. So U and P are dependent variables, meaning that those are the things that we are trying to find. P star is force divided by area. Okay? So the dimension of that is nothing but this. Okay? So you can go through to find this. Last time drag was proportional to rho U squared R squared. That's why we make a non-dimensionless coefficients divided by like this, right? And the pressure is drag divided by area, which is R squared. So I have to divide by R squared. So this is dimensional pressure, and then dimensional pressure has to be rho U squared. Okay? So you can easily check, that is dimensionless. So all the variables with the stars, so variables with this are dimensionless. So next step is just, replace U by U star and X by X star and so on. And so the first one, so first, the term U is capital U times U star. So I have U du star, and then I have to have a T star. To do that, I have to divide by the characteristic time. So T is T star by this. So I have L divided by U here. Okay. I replace T by T star times L divided by U. So that is constant, so I pull out. And then the next term, also this gradient has a star, because I take a derivative with respect to x star and y star and z star. Okay, so this can be a vector. This is a vector again. And here, since I have a u here and u here, so when I use u star, I need a capital U squared. And then I need a gradient. Gradient means, I divide by length. So I need what? L here. Do you know what I'm doing? So basically, I have this term. U is capital U times U star. T is from here. L divided by U times T star. Right? And so capital U and L divided by capital U are constant, so I can just pull out. So I have U, L divided by U, and then I end up with U star, T star. Okay, that's what I wrote here. What is the next term? I have one over row here, and then I need this. So P is non-dimensionalized with respect to row U squared from here. So P is row U squared times P star. And then I divide by L here. Okay? And then I have nu here. And then I need delta star squared U star. So I need a capital U divided by L squared. Okay? And then I have a gravity G here. So then I divide by U squared divided by L. So this is nothing but this. Okay. And then I end up with this guy. This is the same. Right? And then rho cancels out. And I divide by U squared of L, so this guy goes away. Okay? And then this term, what I end up with nu, I divide by U squared divided by L, so I end up with the UL. Okay? So I divide by this by this, then I end up with this. And okay? And then I have G divided by rho. Basically, G is in the only in the Z direction, so I can write this as the G is minus G E Z. Okay, meaning that the gravity is only acting in the vertical direction in the with a negative sign, so I can rewrite this as G divided by rho U square L here and EZ here. Okay. EZ is a unit vector in the Z direction. So now, when we non-dimensionalize Navier-Stokes equations, this guy is nothing but 1 over Reynolds number. Okay? This guy is nothing but 1 over Froude number squared. Okay? So through this, we'll see again, when you solve these dimensionless equations, your solutions will depend on Reynolds number and Froude number. Okay? So that's exactly what we got from dimensional analysis. So U star, so it's a Eulerian velocity, will be a function of x star and t star, of course. But that solution depends on two parameters. One is Reynolds number, and the other is Froude number. So these are independent variables, and these are the parameters involved. So once you fix one Reynolds number and one Froude number, then U will be a function of space and time. That's what I mean by this. And likewise, P will depend on Reynolds number and Froude number. On the other hand, this guy, continuity equation, it will give you, because you have U divided by L and just divided by whole thing by U over L. So this is so now when you solve the problem numerically, all you have to change is Reynolds number and the Froude number. You don't have to change the viscosity or density, length, or speed. You don't have to do that. You just change Reynolds number and Froude number. Those are the only two things that you change in the code. Then you cover a wide range of problems. So typically, what you want to solve is this guy. Numerically, this guy and this guy. Okay? So if you know, the length of ship that you're interested in and so on, if you have to look at only one, condition, then you don't have to do non-dimensionalized because you don't have to change, physical variables. But if you have to cover a wide range of physical variables, then the better way is to use dimensionless, non-dimensionalized Navier-Stokes equations and non-dimensionalized continuity equation. Okay. So is it clear how to non-dimensionalize equations? And the one thing that you notice is, here, this is the magnitude of this, left-hand side, which is, basically acceleration. Okay. So since originally I had the rho times, this term, so I have mass times acceleration, and but I divided by rho first, and then I divided by u squared over L. So basically what you see here, this guy is really measured between the viscous term and this acceleration term. Okay? So 1 over Reynolds number, we got that from viscous force divided by inertia force. Okay? So Reynolds number really measure, the relative magnitude between inertial force and viscous force. So this guy tells us Reynolds number is inertial force divided by viscous force. It is inertial force because it is from mass times acceleration. Okay? And this is I said a viscous force because it's a viscous surface force through friction. So sometimes Reynolds number can be very large. Sometimes Reynolds number can be very small. And if Reynolds number is much greater than 1, so like 10 to the 7th and 8th, then the inertial force is much more important or is dominant. It's much more important than viscous force or inertial force is dominant. On the other hand, if Reynolds number is much less than 1, then viscous force is dominant. So the next question is how large Reynolds number should be so that we can neglect viscous force, which is much smaller than inertial force, or how small Reynolds number has to be so that we can neglect the inertial force. There is no clear cut between this, but if Reynolds number is 10 to the like 10 to the 6th, then or larger, then we say inertial force is much more important, so that we can neglect the viscous force. On the other hand, if Reynolds number is order 1 or 10 or less, then the viscous force is much more dominant. Then we can neglect the viscous force. So in this case, since this number is so large, 1 over Reynolds number is very, very small, then we can neglect that, and then we end up with Euler equations. So I just wrote, the dimensional equation here. After I drop, that. After I drop, this term. On the other hand, if this guy is very large, and then this term is really negligible compared with this guy, and therefore I can write this guy, the left-hand side equal to 0. So this is as you will see, Euler equations. That's our main interest in this course. And then this is called, Stokes equations. So here you really drop, inertia. And once again, Reynolds number is defined U times L, rho UL divided by mu, or UL divided by nu. Okay. Once again, nu is order of 10 to the minus 6. Okay. So U is 1 meter per second, L is 1 meter, then it's 10 to the 6. It's pretty large. Okay. So for this, L has to be extremely small, or U has to be extremely small, which means the body has to move extremely slow, or body has to be very, very small. So nowadays, fluid dynamics has been used for bio applications, and in that case, the microorganism can be very, very small. Then the Reynolds number can be order 1. And then people use these Stokes equations, okay, to solve such problems. But for our applications, dimension is pretty large. L is large, so Reynolds number can be easily 10 to the minus 9th and 8th and so on. Okay. So in that case, you could drop this. But there is some caution about that. This is true. We use global the characteristic length and characteristic time, and if you're really close to the body, and then here the viscosity plays a role. But if you're away from body, then viscosity doesn't play much role. But if you're near the surface, then you have to include viscous effect, even though Reynolds number is large. Okay, and that's what the boundary layer theory is. What the boundary layer is, and later we'll talk about boundary layer theory. But the bottom line is, when Reynolds number is large, very close to the surface or body, the viscous effect is still important. Okay, so here viscous effect or force, viscous force is negligible. So away from the body, viscous force is negligible, but inside thin region, a small region, viscous force is as important as the inertial force. This is a picture when Reynolds number is large. So this is a Reynolds number is much larger than 1. Outside of this thin region, which we call boundary layer, viscous force is negligible. Inside of boundary layer, so this is a so-called boundary layer. Inside of boundary layer, the viscous effect is as important as the inertial force. But away from, the body, then viscosity is negligible when Reynolds number is large. When Reynolds number is small, then viscous force is dominant everywhere. I'll talk about this a little bit more, when I talk about, boundary layer and so on. But the bottom line is, the thickness of a boundary layer depends on the Reynolds number as well. So if Reynolds number becomes, larger and larger, then the thickness of boundary layer becomes, smaller and smaller, as you expect. Because the, inertial force is dominant as Reynolds number is large. Therefore, the viscous effect is confined in a very narrow region. So as Reynolds number increases, boundary layer thickness decreases. But we cannot completely neglect, viscous effect, even though Reynolds number is large. So for example, if you pull the body, if your Reynolds number is 10 to the 9th, for example, then based on this argument, viscosity is negligible, then you shouldn't, have any difficulty to pull, this guy, right? But in reality, you always feel, the drag. And the reason is because you have everywhere else, viscous effect is negligible, but inside, very thin layer, viscous effect is important, and that gives, the friction and drag. Okay. Also, the viscous effect plays a role in the determination of so-called foam drag, which is related, some separation of flow, which we'll talk about later as well. Okay. But frictional drag and foam drag cannot be explained without, the viscosity. And so this is almost true, dropping this, except, this thin layer. Also, there was another, parameter, which was, the, what was it? GL divided by U square, right? This is 1 over Froude number squared. So depending on the Froude number, you can neglect this term or not. Okay. So when do you have a Froude number? Another parameter that we have is dimensionless parameter is Froude number. So Froude number is defined by U divided by GL, square root of GL. So this is 1 over Froude number squared, as I wrote earlier. So this is a measure between inertial force and gravitational force. So if Froude number is much greater than 1, then gravity is negligible. If Froude number is less than 1, then gravity is important. less than 1 or order 1. So when does full number become large? G is fixed. L you have body, so you have already dimension. So when the body is moving very fast, and the full number increases, and then we said this is a ratio between inertial force and gravitational force. From there we divide by this full number is the ratio between these two. Therefore, gravitational inertial force is dominant over gravitational force. Okay, so if surface ship is moving really fast, and the gravitational effect becomes smaller and smaller. Okay, but on the other hand, if the full number is order 1 or much less than 1, then gravity is important. So for example, as an extreme case, if U is 0, if nothing is moving, if the ship is not moving, and then full number is what? 0, meaning that this guy is much bigger than this, of course, because the ship is not moving, so there is no inertial force. And in that case, you have to include this guy and this guy, because U is 0. That's nothing but the hydrostatic approximation. Okay, that gives buoyancy and so on. But if you have a planning hull, or if something is moving very fast, then gravity can be negligible. There are many other physical dimensionless parameters when you include surface tension and temperature and so on. But for us, full number and Reynolds number are the most important physical dimensionless parameters. Okay, so you have to understand what the meaning of full number and Reynolds number. Okay, so for the last review, last subject for review of fluid mechanics is vorticity. That I'm going. So that's what I'm going to discuss next. So vorticity is some quantity we defined by curl of velocity vector. Okay. So this is curl. I hope you understand what it means. It means ddx, ddy, ddz, and ubw. So x component is minus dv dz, right? And so omega vorticity is a vector. Ey is du dz minus dw dx. And plus Ez is dv dx minus du dy. So x component can be obtained by doing this. The y component can be doing from here, and so on. For a two-dimensional flow in the xy plane, meaning that the two-dimensional flow means you have only u and v component in the xy plane, and also anything when you take a z derivative of anything, that is 0. Okay, that's what I mean by two-dimensional flow. So this dot can be anything. And then this guy is 0, w is 0, and flow shouldn't depend on z, so this guy is 0, and this guy is 0, this guy is 0, and therefore you have only z component. So I can write this as a omega x e x and plus omega y ey plus omega z ez, right? There are three components, but in this case, omega x component and omega y component is 0. And you have only one component, non-zero component, which is omega z is dv dx minus du dy. So this is a x, and this is y. So I'm looking at a flow on this plane, on this whiteboard. Nothing moves in this direction. There's no dependence in z direction. Okay, and then I do have only z component. Z is this component. So I have a vector which pointing in the z direction. So that has to be related to some rotation. Okay? And that's why this is called, the rotational vector over vorticity. So let me give you an example. So if I check, vorticity, if this is my velocity field, in other words, if my velocity, u velocity increases in x direction and decreases in y direction, vertical velocity decreases in y direction. If this is case, then I know omega x, omega y are 0. Omega z is what? dv dx. V doesn't depend on x, so 0, and u doesn't depend on z either. It doesn't depend on y, so this guy is 0. So I don't have any vorticity. So that says, some flows can have vorticity. Some flows, don't have any vorticity. Okay. here I put minus sign to make this flow realistic. If I have plus, I'm in trouble, right? Why? I didn't write v plus y. Still I have a zero vorticity because v doesn't depend on x. But I put minus sign, otherwise then I'm in trouble. The reason is there's a continuity equation. So du dx is 1, dv dy is minus 1. So then when I sum these two up, I have a 0. So any flow field, incompressible flow field, must satisfy this continuity equation. If not, then the velocity field is not for compressible flow, or not for incompressible flow. It could be compressible flow. So when we talk about incompressible flow in this class, you have to check whether your velocity field satisfies continuity equation or not. So this time this is a realistic the velocity field in the sense that it satisfies continuity equation, but vorticity is equal to 0. Another very simple example that I often use is this. Right? And this guy also satisfies continuity equation because u doesn't depend on x, v doesn't depend on y, and the vorticity is 1 minus 1 is equal to 0. Correct? I'll just change the sign. Which one? Let me change the sign of u. Still satisfies continuity equation. If I check the vorticity, dv dx is 1 minus du dy, which is another minus 1, so I have 2. So this is not equal to 0. So if your flow field doesn't satisfy, your flow field has 0 vorticity, then we call these flow fields irrotational. Meaning that vorticity is identically 0. I use just example for two-dimensional flow, but in three-dimensional flow, vorticity, all the three components have to be 0 for flow to be rotational. On the other hand, if you have a flow with a non-zero vorticity, then it's a rotational flow. So you call the flow is rotational, and any of those components could be non-zero. Okay. I just define the rotational flow and rotational flow, and also I said vorticity is somewhat related the rotational fluid, but I didn't show exactly what I mean by that. Okay, so I'll just use this example to show what happens if you have a such a flow field. So this is x and y field, and think about some rectangular box. This is a fluid, and if I look at the v component at 2 points here and here, then what happens? Here, these two guys have a same u velocity because y coordinates are the same, y is 0 or the same y coordinates, right? So u components are the same. So what happens if these two guys move like this? Okay, so this, if I have a flow element, a fluid element like this, then this guy just moves. No, not that way. No, sorry. U is the same, the y is the same, so this guy is moving with the same speed like this. Or in this case, in y0, they will stay in the x direction. On the other hand, the v component, this guy, if I look at these 2 points, which one is moving faster? X is large for this particle, so this guy moves faster than this guy. So what happens is, this guy will move like this. Make sense? So I have a UV component. Each fluid particle has a UV component. U depends on Y. So if I look at these two, let's call A and B points, these two have the same U velocity. So if I have this guy will move like this. And also this guy has a V component, but they are different because, the x coordinate of B is greater than x coordinate of A, and V is proportional to X. So what happens is this guy will move faster. So so later, if I look at this, the rectangular box, a rectangular area, this line will rotate like this. What happens to this guy? So I'm looking at A and C this time. These two guys have the same x coordinate. So vertical velocity is the same. If I look at the u component, y is bigger here. So what happens? This guy, compare, the u velocity, this guy is a negative, and the magnitude is larger. Therefore, this guy would rotate this way. So at the end, you will see something like this. Although, okay. So this component AB rotate in this way, and this guy rotate in this way. So whole thing is rotating with this velocity field. Make sense? And so basically the omega z is defined by omega z is the vector in the z direction is defined by dv dx minus du dy. Okay. And dv dx is rotation rate. So theta ab dot. So how fast this element AB is rotating is measured by dV dx. How this AC, this element is rotating in the counterclockwise is theta AC dot is measured by minus du dy. So basically vorticity is 1/2 theta AB dot plus rotation rate. So this is the mean rotation rate. You can show this, by using Taylor expansion, but I'm not going to do that, here. Just tell you that the dv dx is if you look at the dimension, what happens is L divided by time divided by L. So it's 1 over time. So this is, the dimension of the angular velocity. So that tells you, how fast this guy is rotating. And this term tells you how fast this guy is rotating in the counterclockwise. We always, consider counterclockwise to be the positive direction. And then we take the mean of these two. That is nothing but the rotation. So this is what happens. U is minus y, and v is x. On the other hand, the second case, almost the same, but I changed the sign for u, okay? Then I said, the vorticity is 0. So let's look at A, B, and AC. These two guys, vertical velocity is proportional to x. So since the x coordinate of B is greater, so this guy is moving faster than this, so it will rotate like this. So I still have this. But what happens here? U is greater here. So this guy is greater. The U velocity is greater here. So what happens is this guy is rotating in this way. Previously, I have a negative sign, so I rotate this way. This time, I have a plus sign, so this AC is rotating counterclockwise. So by just changing, the sign, this guy is rotating, whole thing is rotating this way, but this time, this AB component line is rotating in the counterclockwise. This guy is rotating in clockwise direction. And therefore, by definition, this guy and this guy is the opposite direction. Okay, one is positive direction and the other is negative direction. So this guy becomes 0 as we discussed. Okay. So at this time, direction is important. One is rotating in counterclockwise, the other is rotating clockwise, and therefore the rotation, the vorticity is equal to 0. Even though each line is rotating, to talk about rotationality or irrotationality of flow, you have to look at the mean value between these two lines. So if we have a flow like this, then we say, oh, this flow is rotational. If we have flow like this, then we say this flow is irrotational. Since we started to talk about the first two and last two, so why don't you look at the first one? And this time, if I look at A and B, this guy x coordinate is greater. So what happens? B will go here. So this is a new position. And on the other hand, C is smaller. It moves down because it has a negative sign, and therefore C will go here. So at the end, the shape changes, but there is no rotation. So it's irrotational. This guy didn't rotate because the V components are the same. The V velocity is the same because they are at the same y coordinates. So as you can see, the area the shape has been changed, but the area is exactly the same because it's a conservation of volume for incompressible fluid. So if I put plus y instead of minus y, then I said it violates continuity equation, right? Which means if I do that, then this guy A point will move here, and C point will move here instead of moving down. Then the area is bigger, which is not allowed, okay, for incompressible fluid. So this is wrong. This is the picture. The shape changes, but the area has to be the same. So this is what happens for U is X, B is minus 1. So the next time, I'll talk about the consequence of rotationality, and after that, we'll start to look at the flow around a body, bounded fluid first, and then we'll talk about flow around the body in the presence of free surface later. Okay. Okay.